Hi guys, my name's Lauren Smith. I'm a 625 point student and I'll be taking you through to 2019's higher level question 10. Today's long question is all about the wave nature of light and sound, and it's worth 56 marks. So, let's get into it. Okay, so bringing us back to our question 10, we are to explain the terms diffraction and interference. So all we need to do is just give out our definitions. The first one being diffraction. Diffraction is the sideways spreading of a wave into the region beyond the gap or around an obstacle. This definition will get you 6 marks, 3 marks for saying that it comes about due to the sideways spreading of waves, plus another 3 marks for mentioning that this happens into a region beyond the gap or around an obstacle, giving us 6 out of 6. Now, interference is when waves from two sources meet, and a new wave is produced such that the displacement produced at any point by this wave is the algebraic sum of the displacements that each wave would produce on its own. This definition, including the key phrase that when waves from two sources meet, because this is when interference happens, it's a characteristic of all waves, will get you 3 marks, giving us 9 out of 9 for this definitions question. I just want to point out that normally, or sometimes with definitions in physics, either the verbal definition or, in fact, maybe a more mathematically based definition is allowed in the marking scheme. The key difference is if you are to state a law, that means that a law is normally in mathematical form in physics. So therefore, a verbal explanation of that law or the mathematical explanation is given. However, we're to explain terms, and these terms don't really have a strict mathematical law or description with them. So you are to give a verbal definition. Coming back to the original question, we are told that Thomas Young in 1801 performed an experiment to demonstrate that light is a wave. Now, there was a little bit of a debate on at this time beforehand as to the fundamental nature of light. Newton proposed a theory that light was made up of particles known as corpuscles, and because Newton was such an incredible scientist, a lot of people were skeptical or fearful to go against his theories. However, Young and many others like him in this era performed experiments and built up that load of evidence that suggested that light is a wave. Nowadays, we know that Newton wasn't wrong. Light is made up of particles, but light also has a wave-particle duality, which is beyond the scope of this Leaving Cert course, but it's very interesting to look into. It's one of the fundamental concepts of quantum mechanics. So Young passed monochromatic light through 2 narrow slits and observed a series of bright and dark fringes on the screen. And we're to explain with the aid of a label diagram how a series of bright and dark fringes were produced and how does this experiment demonstrate that light is in fact a wave. Okay, so going into our explanation with our label diagram, please don't forget to label it, you will lose marks. And as you can see here, I always have an overabundance of labels here just to illustrate my point. Now, here is the diagram. It's very, very important to have a good diagram. A picture speaks 1,000 words. But always, if you're not the best artist in the world, like me, I wouldn't be drawing this out in an exam in this level of detail, not at all. It is, though, best to label your diagram to show the examiner what you mean. So, like I have here, most important features of the diagram would be our Young slits. They're key, and showing here with your diagram that diffraction occurs after these slits. So we've got 2 new waves produced at S1 and S2, these 2 new sources of waves, and we also have a screen full of dark and bright fringes which illustrate an interference pattern. Also, what's key in the diagram is that we have a monochromatic light source. It is a light source of 1 wavelength, and this is what was stated at the start of our question as we went through. Okay, so this is the diagram, and the explanation or the description is as follows. Monochromatic light shines onto the first narrow slit, undergoing diffraction and illuminating the pair of slits S1 and S2. Again, you're just walking the examiner through what you've drawn on the diagram. Now, I just want to mention that S1 and S2 must be coherent sources. Coherent sources must have the same frequency, and the 2 waves which are produced from those sources must have a constant phase difference or they are in phase. This is the case in this experiment because S1 and S2 both originate from our original monochromatic light source. So they come from the same light source, therefore they're both going to have the same frequency, and of course they're going to be in phase as well through this. Now, diffraction occurs at each of these slits. Interference occurs in the region beyond these two slits, and since S1 and S2 are coherent sources, there's an interference pattern produced on the screen as shown in the diagram. I'd always throw in an as shown in the diagram when I'm going through my explanation, because it does ask you to always refer back to the diagram. You're to explain with the aid of a label diagram. That's very important. Now, the interference pattern consists of a series of parallel bright and dark lines, and these are known as interference fringes. So it's important to actually explain what is to be observed if you conduct this experiment. So the method is very important, but what you observe is of the utmost importance in physics. Okay, so where do you get your marks? That's the important part. You get 3 marks for including your slits and the arrangement of that. You get 3 marks for showing that diffraction occurs at these slits, and of course you'll get 3 marks for saying that interference occurs, giving you 9 out of 9. Okay, and we were asked, how does this experiment demonstrate that light is a wave? Now, this ties in keenly to what we observed in this experiment, which was that the pattern of bright and dark fringes come about as a result of constructive and destructive interference, respectively. A bright fringe occurs when crests of the wave meet other crests of the wave, or when troughs of the wave or minima meet other troughs of the wave, and then the amplitude of the resulting wave is doubled, it's increased. And a dark fringe comes about when, say, a crest or a maximum of the wave meets a trough or a minimum, and they cancel each other out, and the amplitude of this resulting wave is in fact 0. So therefore, the pattern observed on the screen can only be explained by interference, which is one of the phenomena characteristic to waves, i.e. it can only be explained by interference, and interference only happens to waves. Explaining this will get you 3 marks. So all we need to do now is just move back to our question, and we're told that this experiment was repeated in the school laboratory, but with the following extra bits of information. So the slits were 0.5 millimeters apart. They were placed at a distance of 1.25 meters from the screen. The distance across 13 bright fringes on the screen was found to be 1.65 centimeters. We're asked a couple of questions on this. Now, before I move on to the next part of our question, I just want to draw your attention to page 59 of the Formula and Tables book under the topic of light and sound. In particular, we're going to be looking at the diffraction grading formula. Now we're asked to calculate the wavelength of the monochromatic light. And I've drawn a diagram illustrating the problem and indicating what variables we need to solve for. And the target variable in this case is in fact lambda. Okay, it's going to be the wavelength. Just a little disclaimer, this diagram is clearly not drawn to scale, as you can see from the units of measurement, okay? But it doesn't matter. It illustrates my point, okay? So we need to find lambda, the wavelength. So we're going to have to keep this formula in mind, which is n lambda is equal to d sine theta. So I'm putting it up here just as a quick reminder. This is what we're looking for. And this can be rearranged to get lambda is equal to d sine theta over n. Okay, so we need lambda, so we need to find d, theta, and n. What are these? Well, d is the distance between the slits, which we were given quite nicely, which is 0.5 millimeters. However, I would be inclined to convert them into SI units, like I did in the diagram, which gives us 0.5 times 10 to the power of minus 3 meters, okay? Now, what is n and what is theta? Theta in this formula is the measure of the angle between the 0th order image and the nth order image. So it would be from here, the middle, all the way up to here. We have 13 bright fringes. That means we have 6 bright fringes or order images on either side of the 0th order image, which is here, and therefore n is equal to 6. What is theta? Now, theta can be obtained from the trigonometric identity. Tan of theta is equal to the opposite over adjacent. We can do this because, like I've drawn in the diagram, we can split this up into a trigonometric problem, which is why it's always so important to draw a diagram. It can help you see clearly what you need to solve for, what's going on. Now, what is the opposite and what is the adjacent? The adjacent, as we know, is the distance from the slits to the screen. That is simply 1.25 meters. The opposite, however, is half of the distance across the screen, because we are looking at the triangle from this point up here to this point down here. We were given the distance between the 13 images as 1.65 centimeters, which is just 10 to the power of minus 2 meters. I'm just going to convert everything into meters. It's just easiest for everyone. Now, in order for it to be the opposite of the triangle, we're going to have to divide it by 2, giving us 8.25 times 10 to the power of minus 3 meters as our opposite. Okay, so all we need to do is just sub it into the formula and we can get our answer. Now, if you rearrange the formula and substitute everything in, you'll get theta is equal to tan inverse of 8.25 times 10 to the power of minus 3 over 1.25. And let's just put this into our calculator and see what happens. Now here, looking at my calculator, I have my calculator set in degrees. So my answer for the angle will be in degrees. If you had your calculator set in radians, your answer is going to be in radians. Just be very careful. Okay, now just double checking, do I have everything right in here? And I do. Always double check when you're putting in your answers into the calculator. Hitting that equal sign, we get 0.378 degrees as our angle. It's a very small angle, and I'd round to 3 decimal places. Okay, so we have the angle, we have the distance between the slits, and we have the value of n. Now we can finally find the wavelength of the monochromatic light. Let's substitute everything in, and we'll finally get our answer. Now, getting up our calculator, if you have left your calculator in the exam, never delete any values, never turn your calculator on and off when you're midway of a calculation, because this value here is stored as an answer. So when you're inputting this expression into your calculator, as you can see here, the argument in the sine function is just the answer. So we don't need to write it all out again. We're going to get a very, very accurate answer, which is always key. Hit that equal sign, and we're going to get a wavelength of 5.499 times 10 to the power of minus 7, which we can round, and I'd encourage you to do so, to get our final wavelength as 5.5 times 10 to the power of minus 7 meters. Before I move on to another part of our question, I just want to go through the marks for our question. You're going to get 12 in total, 3 marks for calculating correctly the opposite, or noticing that the distance that we need to calculate between the 0th order image and the 6th order image is 8.25 times 10 to the power of minus 3 meters. Now, if you mention or take down the tan formula, if you substitute your values into the tan formula like over here, or indeed if you get your correct answer for the angular separation, you're going to get 3 marks. But even without doing any calculations whatsoever, if you just put down that tan identity, you're going to get 3 marks. So always put down the formula. Moving on, you're going to get 3 marks for mentioning this formula up here, the very important diffraction grading formula. Or you're going to get 3 marks either way. If you substitute your values into that formula, either of these two will get you 3 marks. And finally, you will get your final 3 marks if you get the correct wavelength, giving you 12 out of 12. Okay, so looking at the next part of our question, we are to list 2 adjustments to the apparatus that could be made to increase the distance between the bright fringes. Distance between the fringes is related to the angular separation of the bright fringes theta. So with the help of the formula, we're going to look at it and guess, okay, if you have no clue on the exam, the formula is going to come in very handy, because you can look at the formula and say, okay, what things can I adjust in the apparatus that will increase the distance and therefore this angle? And we're going to look at the wavelength here and the distance between the slits. It follows that if you decrease the distance between the slits, then theta will get larger, because we have from the formula here, 1 over d is directly proportional to sine of the angle theta. For our second one, if you increase the wavelength of the monochromatic light source, that increases the distance between the bright fringes, as we have here, as seen in the formula, that this is directly proportional to sine of the angle theta. Now, through approximations and geometrical analysis of the problem, the distance between the slits and the screen, which I'm going to label as R, can be said to be directly proportional to the angle theta. And therefore, if you move the screen from the slits, you'll increase the distance between the bright fringes. Okay, where do you get your marks? You get 3 marks per correct adjustment, and you need to list 2. So you get 3 plus 3. Tip, put down as many as you know. If you know 3, put down 3. If you know 4, put down 4. If you know 2, put down 2. If you know 1, put down that 1. And maybe look at this formula and your diagram to see, okay, what potential things can I just always put down an answer? It may turn out to be correct. Okay, so scrolling through the last bits and pieces of our question, we are given a little bit more information about Jung. We're told that he was a polymath, he had many other interests, including the discovery of the purpose of the ciliary muscle in the eye, amongst other things. Now, we are asked a couple of questions on this. We are told when the ciliary muscles contract, the lens in the eye becomes thinner, and we are asked what effect this has on the power of the lens. Before we go on to that question, I just want to draw your attention to page 60 of the Form and Tables book, in particular, the formula for the power of a lens. So the power of a lens through to this change of the ciliary muscles is affected as follows. The power of the lens is in fact decreased. This can come from the formula P is equal to 1 over F, where F is the focal length. If you have the lens in the eye becoming thinner, any lens that will become thinner will have a larger focal length, and since it has a larger focal length, the power is going to decrease due to this inverse relation here. This explanation will get you 3 marks. Okay, so just going back to the original question, we are told that a certain musical instrument can be modelled as a cylindrical pipe that is closed at one end and whose length can be changed. The air column in the pipe vibrates at a frequency of 512 Hz, and we're asked a couple of questions on this. We are also told that the lengths of the pipe at the first 2 positions of resonance are 16.7 centimeters and 49.8 centimeters. We are first asked to draw diagrams to show the first 2 harmonics of this instrument. Because we were dealing with a closed pipe, only the odd numbered harmonics are present. Therefore, the first 2 harmonics are the first harmonic and the third harmonic of this musical instrument. Now, just to note, when you are drawing harmonics in a closed pipe, at a closed end, you will have a node. At an open end, you'll have an antinode. At the first harmonic, we have to draw the pipe at the easiest configuration of this rule. The easiest configuration, or the simplest one, in which we would have a node at the closed end and an antinode at the open end, is exactly as I've shown in the diagram to the left. One node, one antinode will have a quarter of a wavelength in the pipe. Moving on to the third harmonic, we're going to have the next simplest configuration of this rule, where we would have a node at one end and an antinode at another end. And this would mean we would have a node, antinode, node, antinode. Now make sure to label your nodes and antinodes. I've done it with an N and an A for node and antinode respectively. However, if you are doing it with just initials, I would recommend putting a little key at the side like I've done over here. Okay, so where do you get your marks? You'll get 3 for a correct diagram for the first harmonic and another 3 marks for your correct diagram for the third harmonic. Before we dive into these calculation questions, I want to draw your attention to page 59 again of the Form and Tables book, but this time to the velocity of a wave equation. Given the different lengths at which the first and the third harmonics occur, or the first and second position of resonances occur, we need to calculate the wavelength of the sound wave. Now, before we get into any direct calculations, I want to note that when you're going from a node to an antinode, it corresponds to a distance of the sound wave of a quarter of the wavelength of a sound wave. Therefore, for the first position of resonance, it equivalates to the first harmonic. It will equivalate to a quarter of this wavelength. And therefore, at the second position of resonance, which equivalates to the third harmonic, this length of the pipe will account for 3/4 of a wavelength. I just want to note that if you take away the length of the second position of resonance from the first position of the resonance, you're going to get a half a wavelength, because 3/4 of a wavelength minus a quarter of a wavelength is going to give half of a wavelength. But we want 1 full wavelength, so we're going to multiply this whole thing by 2, and this will give us the wavelength of a sound wave. Okay? Now, we know that the length of 3/4 of a wavelength is equivalent to 49.8 centimeters, or 0.498 meters, and that is taken away from the length of a quarter of a wavelength, which is located at the first position of resonance, which is 16.7 centimeters or 0.167 meters. It is preferable to always keep your answers in SI units rather than in centimeters or any other unit of length. Okay, this is going to equivalent to our wavelength, so let's put this all into the calculator. So we have 2 times 0.498 minus 0.167, using brackets to multiply out our values so that the calculator doesn't get confused. Press that equal sign and we get a total wavelength of 0.662 meters, which will give you 3 marks in total. So that's part 1. Now part 2 is asking us to calculate the speed of sound in air. We have the frequency. We also have the wavelength. Now to get the speed of sound in air, we can use the formula. C is equal to F times lambda, or the formula to find out what the velocity of a wave is. C is going to be the speed of sound in air. Okay? And this is why it was preferable to have our answer for part 1 in meters. So when we're converting from one quantity, i.e. hertz and meters, to another quantity, speed or meters per second, we don't have to do any conversion there. Okay? Now let's substitute everything into this formula. Now, substituting into your formula is very important because you will get 3 marks either for mentioning the formula itself or substituting your values actually into the formula. So always do that. That'll get you 3 marks. And the final 2 will get you your answer. So let's put that into our calculator. We have the frequency, 512, times the wavelength, which is 0.662 meters. Hit that equal sign, and we get, for the speed of sound in air, 338.944 meters per second. Or, rounding to 3 significant figures, we get the speed of sound in air to be 339 meters per second. Please do not forget your units. You will lose marks if you forget them. But if you don't forget your units, you get 2 marks for your correct answer at the end.